Okay, so first I'll demonstrate the model which I will use. So as you can see, this is a single stator, single rotor configuration, 12 slots and 7 pole pairs. Concentrated winding. So in this case I use 8 turns for the winding. Okay, I'll change slot fill factor a bit. And just to speed up simulation, I use only one cylindrical slice in this case. Okay, let's start with just a simple magnetic simulation without eddy currents, of course, without AC winding losses. So I set up the medium accuracy, 48 points per 1 electrical period. Yeah, simulation took 43 seconds. And let's make a snapshot of it just to compare with a transient FEA simulation with AC losses in winding. Okay, I'll save it as a separate file. Unlock it to make changes. And we'll import the stator geometry from step file. So this is a step file for this motor. The program automatically detects 12 slots and also automatically detects the area for the tooth and the coil. Here we also can switch off parts of the rotor which we don't need, and on the right we can see the cross section of the tooth, and now here we can assign the material types for each subdomain. So here we select the winding subdomains, and in this case we use the full winding model, which means the geometry includes all the turns and strands of the winding. Another option is a lumped model, where the coil is a solid body. So this program also automatically determines the options for the number of turns and number of slots, depending how many subdomains were assigned with the winding material type, and also how many winding layers we have, and what is the orientation of the layers, left, right, or upper, lower. So in this case we use 8 turns and 1 strand option. So now the we can see each turn imported from the DXF.
Okay. So basically, if I understood correctly, you're still following the winding scheme that you have as per default.
Yes.
But then assigns the current directions for each turn then automatically, because now you can from the import you know where the turns are, as you can see there. Yeah.
Yes.
Very good. Interesting.
So let's also look at the mesh. So now you can see that it's meshing all the turn separately. So it automatically detected that the winding has 8 turns, and and I also used just one cylindrical slice for this model just to speed up simulation.
By the way, can you edit the mesh on the conductor itself? Do you have a command if you want to make it thinner?
To make it thinner, we can limit the triangle size.
Okay.
The minimum.
So you do it. Okay, you go to a global. It's not local yet. Okay.
Yeah, and for local, if you would like to make mesh finer locally, I usually add some gap between the conductors here.
I'm just saying because since now that you have a transient solver, for sure, I imagine, let's say through MATLAB, you can input as well a non-sine wave current input. And eventually, if you want to simulate PWM, you go to the skin depth of the conductor, and therefore, it will be interesting to have a skin depth mesh as such. Not sure if for you to implement it, if you are thinking to add a tool just to have a skin depth mesh, or eventually execute a piece of code in MATLAB to put it, or did you think about this? I mean, if you want to have a skin depth mesh on each turn of the coil, right? Let's say in case that you want to simulate instead of have a sine wave input, you are imputing a current with let's say with a certain switching frequency coming from the power converter, and therefore you want to understand the eddy currents on the, let's say, on the edges of the conductor, and therefore for that you need to have a skin depth mesh. So it's not just being a thin mesh; it's a skin depth mesh, which is a different feature. Is it something that you can do now, or eventually that you can thinking for the future?
Just let me show you something.
Yeah.
So I have another model for the same motor with. Is this what you mean? Just a finer mesh on the edges of the conductor.
Yeah.
So basically, I just added some gaps between the conductors.
Okay.
And this way, it's giving me much smaller triangles on the.
I see. Although skin depth mesh is a bit different from this, because if you remember, particularly already 2D or 3D, because the layers of the skin depth, they have kind of exponential decay. The way as when you go, for instance, if you have a skin depth mesh with like three layers, the separation between layers as a law you need to follow, which is kind of is following a exponential distance, so it's a calculator. You usually have a calculator to determine this.
Okay, I understand.
But okay, I see that. But it's quite powerful that actually we are doing this. It's already very interesting because anyway, I understand that you are starting, so I'm trying to see how deep it can go.
Yeah, sure. We will consider it for the future. This is just like our first version with the skin effect.
Okay.
Well, can add some features to make the mesh like following the skin depth profile analytical. Okay, let's run simulation for this case. So I'll need to go to dynamic finite element. Time steps similar to that I had for magnetic simulation for 48 points per electrical period. But here I will use about 1.5 electrical periods for this simulation. So I need to go to advanced simulation settings and select script with free-phase current source. Of course it can also be inverter with PWM, but it will take much longer. So for this one I'll just use free-phase current source, and it suggested me to change the simulation script, which should be used with free-phase current source. So all the other settings the same as for magnetic, same current, same speed. So and adjust the time step to be about the same as it for magnetic, and slightly more than 1 electrical period, just to allow for some transients. I forgot to allow saving files just to demonstrate the animation for the eddy currents. Okay, let me start it again. Yeah, the simulation completed. As you can see, it took maybe about a couple of minutes versus 45 seconds for the magnetic. We can review the results. Especially what we're interested is the stator winding losses. So for this one, the stator losses were 208 watt, but when we add skin effect, so the stator winding losses more than doubled with skin effect. And also you can see the torque dropped from almost 21 Newton meters to 16.5 Newton meters. Let's also look at the current distribution in the winding. So you can clearly see the skin effect, especially at the upper turns, which are closer to the magnets. And now let's run the same example, but also adding eddy currents in magnets and also in rotor core. So in this case, assume that the rotor is a solid steel. So default Stamen's iron loss model is not good for this kind of rotor back iron when it's not laminated. So I'll save it as a separate file. I will clear the simulation data, and in order to include eddy currents, I need to allow this option for eddy current calculation. By default it's not allowed because it significantly increases simulation time.
So sorry to interrupt. When you can you leave the mouse on that option? Because when you select that option, okay, calculate the currents in iron core magnets and other. When you say iron core, you mean it's not using the post-processing for core losses, is what you mean?
It will use both. So it will use a transient eddy current model to calculate eddy currents, and it will also use post-processing with Stamen's iron loss model to calculate eddy current and hysteresis losses. So it will use both models.
Okay.
In this case, so we will compare the results from two iron loss models.
Okay.
So let's start simulation.
But of course, in this case, you are just solving eddy currents on the laminations, not hysteresis, right? So.
Yeah, I'll show you 1 second.
Okay.
So, yeah. So once we start the simulation with eddy currents, it will ask you which parts you would like to include for eddy current calculation. So I'll include magnet and core loss and rotor core, but I will not include the stator core because in this case it will be much longer. The simulation will run much longer. So also you can see it automatically detects how many segments for the magnet we have. So we have 3 magnet segments, and we can also optionally add, for example, the stator core. We can enter how many laminations the stator core has in the radial direction. If we allow the stator core, it will use this number for calculation of the eddy currents in the stator core. And for the rotor core, I would like to use just one solid piece of steel. So I click apply button and it starts simulation. And it also uses the same model for the coil. So with eddy currents in the winding coils. Yeah, in this case it will take several times longer. While it's running, I can demonstrate. Okay, I'll demonstrate the simulation script for uneven air gap. To allow the option for unequal air gaps, or to allow the option to change the air gap during the simulation. I'll just need these 2 lines which specify the multiplier for the air gap. So the modified air gap is calculated as air gap multiplied by the multiplier. So we have multiplier for top and for bottom air gap. So in this case, single stator, single rotor, just one multiplier will be used. But if we have double rotor, double stator configuration, so both these multipliers can be used for the air gap, and it can also be changed on each time step. So instead of just static air gaps, we can use dynamic. We can change the air gaps with time if you need to see some effects of this.
That is interesting. So how do you set up that? Because I can see that there is fixed. So if you want to put a dynamic, you mean that you are introducing this multiplier for each time step, is what you mean?
Some function. You can define it as some function of the current time, let's say.
Understand. Interesting.
Yeah, here's the variable for the current time, current simulation time, and we're also outputs output structure, and inside this output structure you can find forces, the axial forces, which you can also use as a, so you can set up the air gap as a function of axial force in each air gap. Let's say
Okay, so based on the net force of the rotor, then the air gap will be updated in the next time step.
Yeah, you can set up this function inside the script.
You need to set up the function, so you know the forces from the structure and outputs, and then from, if you know, you need to know the physics to relate these results from FEA to your dynamic air gap.
Right.
Very interesting.
Right. Yes.
I can see.
Yeah, and since this is a full dynamic simulation with electrical circuit and all the controls, so you can also add some mitigation techniques. So let's say you have two stators, and so you can separately control the current in upper and lower stator, so you can add some technique that to mitigate the axial forces, just to equalize the axial forces on the rotor in case if your air gap not equal. Also useful feature, I think.
So this will be done in an additional script, you mean, or?
Yeah, this will require additional script for the control. So this script, this is a default script for space vector PWM with fog control. So it's implementing the fog control. So you can add your own control, which will be also mitigating the axial forces, let's say. Okay, the simulation is done. It took about 4 minutes. So you can see the eddy current losses and magnets added, and also transient eddy current losses in rotor core. And if we compare it to the default Stamens model, so you can see because the Stamens is a full laminated steel, the Stamens coefficients for the laminated steel, so it's much less than the actual eddy current losses. It's not that much compared to the stator losses, but still it's even higher than losses for the stator. We can also run an animation just to see the eddy currents. Yeah, now of course the current in a stator winding is much higher than in a magnet and a rotor core, so we don't see much difference.
And can you, because I think this plot is unique plot, or can you select the subdomains where you actually want to see the eddy current, the current density? For instance, let's say you want, because of the scaling issue, you can say, I don't want to see windings, but I just want to see magnets. Yeah, or you change the scale, you mean?
Yes, change the scale. So we'll need to adjust the scale. So let's say this one 10⁻⁷. So let's say so this scale is good for magnets, but too small for the rotor. So we see.
Okay, just I understand. Just to see how trying to explore a bit the degrees of freedom that you still have, but is interesting. I think.
Maybe. So this one should be good for the rotor core, because rotor core has a higher eddy currents. Let's look at this. So we can see some eddy currents in the rotor now, and in the stator winding it's just beyond the limit. So just adjusting the scale, we can see the eddy currents in different parts. Yeah, but there's no option to select some part which.
You have an option on the model because I know that you have an option to select the eddy currents in all the other components, but not on the winding. Can you just run it like if it was on the magnetostatic without meshing the conductors? Or?
Yes. Okay. Then I'll need to come back to the first MXA file that I used, or the.
Okay. I got it. Understand. Yeah.
Okay, sure. Let me show you. Yes. Save changes. Yeah, files become quite large, so it takes time to save in them. Because once we add eddy currents, a lot of simulation data in the file. So this is a model when the stator is just created using template. So it's so we call it lumped winding model. So the previous one from the step file was the full winding model when we simulate each turn and each strand of the winding with skin proximity effects. And this one is just lumped, so we do not simulate each turn. So we have 8 turns in each coil.
Yeah, I understand. It's kind of an on-mesh coil setup with the mesh on the slot for you to calculate then the flux linkage through the vector potential. I think that is the way.
Yes.
So yeah. Okay.
So this way, we just do the same setup. And run simulation. So the same dialog. We allow magnet and rotor core. Apply. This one should be faster because we don't have a detailed model for the winding. Maybe 2-3 minutes. Okay, we can review the. You can see the torque is higher because with eddy currents in stator winding, the torque was about 16 Newton meter. Now it's almost the same as for magnetic static. And you can also see the magnet losses a bit higher than it was before, since we excluded the eddy current in winding conductors, so there's no damping effect from these eddy currents in the coils. And also the rotor eddy current losses a bit higher. As you can see, the current in winding just uniform. Okay, do you have any questions? Hello?
Sorry, I'm listening muted, but yeah, I think nothing in particular right now. It's quite very interesting, actually, and seeing the way as we are launching this through the dynamic, actually, and with the scripts that you already have available through the MATLAB version, where actually you can input current with a PWM pattern, right?
Yes.
So actually is even more powerful, because in the end, nothing apart from computational time, nothing stopping us from actually simulating even the effects of the PWM effects on the eddy current losses in the windings and the magnets and
sure. Yeah.
Including in the stator core, actually. That is the part that is impressing me a bit, that you actually are putting a feature available to compute the eddy currents in the laminations itself. So it's quite.
I would say for lamination it's a bit off, because when you calculate eddy currents in lamination, if you consider magnetic field in all three directions, x, y, z, and let's say the lamination is in xy plane.
Yes.
So the part of the magnetic field in that direction starts playing much more important role for eddy current in laminations.
Correct.
Yeah, but since it's a still 2D approach, we can only include xy x.
No, I agree. Agree.
So it's still better to use statements.
For that.
Is a statements loss model or a full 3D calculation? Yes. So it's pretty good for like solid bodies like magnets, and if it's solid rotor core, but for laminations, it's depending how many laminations you have. What I usually do, I usually apply some correction factor, where I just decrease number of laminations. So I look at the statements model results for losses. Let's say for the sinusoidal excitation, and then I correct my lamination model for transient eddy currents, just decreasing the number of laminations until I match the transient eddy currents, with statements, and then I can apply PWM just to see the effect of PWM on eddy currents.
I see.
With transient model.
I understand. And then you can use that kind of as a correction factor for the Steinmetz later on for magnetostatic, because the addition, you can say that.
Sure.
Okay. Okay, interesting. I mean, as I say, it is to start, let's say, on a concept design. When you start, it's very powerful what you're doing here. I think you already know what I think about you. So
thank you.